next part, we are concerned with understanding samples and sample sizes, which is important for hypothesis testing. The objectives for this part are to identify whether a sample reflects a population, to assess how large a sample may need to be within the range of values of a population, and to define where are the limits of interpretation with a small sample size. We are rarely able to know everything we need to know about a population. So we take a sample. A sample is a representative sample of a larger group of people or things with one or more characteristics in common. More often than not, we only have a sample of a larger population to work with. When we look at a sample, we are mindful that it is supposed to be representative of a larger population. This is the goal of inferential statistics, to use the data we do have to answer a research question about a population. When we see the results, they are only estimates of the values of the population characteristics, so we have to be careful. Appropriate sampling allows us to have high confidence in our interpretation. So we need to be able to describe the characteristics of the population as well as the sample. So we must distinguish between parameters for a population and statistics or point estimates for samples. We also have to use different notations. For example, we use mu for the average of a population, and we use x bar for the mean of a sample. Similar distinguishing parameters are used for variance, standard deviation, and proportion. The most important concept in statistics and to make sense of a population is the central limit theorem. The theorem states that the distribution of a sample means drawn from a population will approximate a normal distribution as the sample size gets larger, regardless of the population distribution. The classic example is to roll a die. And if we roll this die and note which face it lands on, and we do this 1,000 times, eventually we do it enough times that the answer will begin to form a normal distribution, which looks like this. In other words, the average of a random sample will closely resemble the average for the whole population as the sample size increases, regardless of the shape of the distribution. That means the more samples included, the more their distribution will resemble the population. Suppose a researcher wants to know the average age of dog owners in the US. The researcher would select a number of representative people from around the country, and that number is smaller than one might think. 30 to 50 is usually enough. The researcher would find their average age, and if the sample is large enough, the researcher would be reasonably sure that the sample average would be close to the national population average. So here I have a random sampler. The black curve that you see here is the distribution of a population. It has a specific mean of 16 and a specific standard deviation. Here it is of 5. I will now show you a video where I draw 5 samples at random. Here you see. I take the mean, and now I repeat this process until I have 30 samples. Every time I calculate the mean, now it's going faster. So, as I have drawn more and more samples and I calculate their mean, the mean the distribution of the mean started to resemble that of the population mean. This is the central limit theorem in action. A population tells us a lot about the random samples from it, as we have just seen. We can compute based on a known population mean and standard deviation the likelihood that a random sample mean and standard deviation came from it. But the opposite is also true. Random samples tell us much about the population it came from. To talk about the variability of the sample means, we use the concept of standard error of the mean instead of using standard deviation, although the two are basically the same. Here is what the formula looks like. The population standard deviation, which nowadays we are getting better at knowing thanks to big data, is divided by the square root of the sample size, which is going to help us adjust for variability. Because of the central limit theorem, a random sample will be roughly around the population mean and normally distributed such that 68.2% of the samples will be within one standard error of the population mean, 95% will be within two standard errors, and 99.7% will lie within three standard error of the population mean. The target population is the one we want to make decisions about, so we can sample the population and use the statistics to tell us about that population. If the sample's mean is more than 3 standard errors away from a known population mean, it indicates it is very rare and likely not taken from that population. This is not necessarily bad news. It might mean we have found a new population. But this is the foundation of hypothesis testing. Let's move on to confidence intervals, which express a degree of confidence that an interval will in the long run contain the population's mean. Confidence intervals have upper and lower limits. By convention, at a minimum, we look for confidence that is greater than 95%, meaning that should you repeat an experiment or survey over and over again, 95% of the time your results will match the results you get from a population. The formula for the confidence is this one, where alpha, this one, denotes the error we will accept. 2.5% of the time, the sample means will fall below the standard error, and 2.5% of the time it will fall above the standard error when we are looking for a confidence interval of 95%. We want to calculate the standard deviation. We also need something called a z-score. Z-score are the number of standard deviations from the mean. A score of 0 would mean a sample score is identical to the mean score. Here I am showing the z-values for the most commonly used confidence levels. For example, if we wanted a 95% confidence, we would use a z-value of 1.96. Okay, let's look at an example. Let's pretend The Economist magazine reports from a study of 300 subscribers that the average income is $80,000 with a standard deviation of $15,000. How close to that would the real average income of all subscribers be with 95% confidence? We can calculate the actual average income range for all subscribers by plugging the numbers that are listed here. And there's a little bit of a overlap here, but that should be 80,000, 15,000. Sample size is 300. Confidence level is 95. And if we plug in the numbers into the formula, we will get a value that is plus or minus around the mean. So we can say, and this is the value we get, and we can say that with 95% confidence, the actual average income range for all subscribers would be between 81,000 and 78,000. Now, if we were to repeat this example with only 20 subscribers, and you can do this by yourself, but if we were to repeat it, and if we did the math, the range of our answer would actually become larger. And that's because our sample size is smaller. And here, if you're interested, is how we go about calculating the solution to the example. So now let's look at the t-distribution, which is something we would use for small samples, let's say less than 30. The t-distribution is similar to the z-distribution. A specific t-distribution depends on a new parameter that is called the degrees of freedom. The degrees of freedom refer to the number of independent pieces of information that go into the computation of the sample standard deviation. As the degrees of freedom increase, the t-distribution will look closer to a normal distribution. So as you can see, here we have a curve with 10 degrees of freedom and with 20 degrees of freedom. And as we add more and more degrees of freedom, it will start to resemble the normal distribution, which is the top line. And if you're uncertain whether to use the t or the z-score, here is a helpful diagram to help you decide. Basically, what it comes down to is this. Can the population standard deviation be measured or known? If it can, use a z-score. If it cannot, use a t-score. As you get more familiar with standard errors, you might notice them being used pretty much everywhere. However, here's a word of caution. We are often overconfident in our ability to measure something we don't know. The population itself is often not known, and overconfidence usually affects experts more than anyone else. So, as you start using these statistics skills, proceed with caution in your interpretations. And here's a summary of this part 2 video. We can use confidence intervals to determine a range by which our sample represents the population. If we know a population standard deviation and a range we want to be able to fit within, confidence intervals can help us estimate the sample size we need. Even with relatively small samples, we can estimate values we expect with confidence. And here is a list of knowledge that you should be able to answer from this video.